You are now, give it back to me. I'm what? What is he? What is he now? And what am I? Excellent, good, thank you. Good, that's a no, I don't have time. That's a very, very difficult concept. And so that's the best way of explaining that. If you have understood that acid-base conjugation, then you will really get ahead of this thing. So now you have, for example, if you have here an acid, could be H2O, is a rather weak acid. Its conjugate base would be OH minus. It gives an H plus off, and this would be OH minus. And H3O plus, if this is an acid, it wants to give off the proton. Its conjugate base would be H2O, for example. And you can do this also here for bases. H2O is a relatively weak base. And what would be the conjugate acid to that? Would be H3O plus, okay? So now, you see that if you have here your acid, we always write this as HA, and you react this with water, you put this in water. Water is a base here now. It wants that proton, and it makes H3O plus. All right, H3O plus, and now this acid has become a conjugate base. What would be that, okay? And now, that was the base. It takes that proton away, and now H3O plus is the conjugate acid of that base, all right? So we can write an equilibrium now. We can write an acid equilibrium. This is this concentration times this concentration, divided by this concentration, divided by H2O, but H2O is the pure solvent. With this we set it 1, and that means it doesn't go into the equation. You see that? So this is the acidity constant. That would be an acidity constant. So if this ray is very large, then you have a strong acid. If it's small, then you have a weak acid. That's the definition of strong and weak acid. You probably heard if it has a low pH, if it makes a low pH, then it's a strong acid. Absolutely wrong. Okay? I can take a pound of weak acid and I make the same low pH than what I make with a couple of drops of strong acid. And you will get the hang of this when I explain that to you. Now you also could formulate a base constant for this. So this would be H2O, okay? And you have your base. So what the base wants the proton from this guy here. So that becomes then the BH plus. That's the conjugate acid. And base we always write as B. And this H2O has given away a proton. It is now OH minus, a conjugate base of this. So this is obviously a base equilibrium. And we say this was A was for acid. We say Kb for base is the concentration of this times the concentration of this divided by the concentration of this divided by the concentration of water, and water is 1. With this we can come to this equation. So that's the acid and that's the base constant. If that constant is large, you have a strong base. If it's small, you have a weak base. Now there is this dilemma with the water, that water can be both. It can be an acid and a base, and it's to itself. So that would be an acid and that would be a base. So this is just two waters. How can that be? They said, okay, that base wants that proton here. It forms H3O plus, and with it becomes the conjugate acid of that base here. Now this acid has given away a proton, and now it is OH minus. That's the conjugate base of that acid. So you have an acid-base equilibrium for water. So water obviously dissociates into H3O plus and OH minus. But remember, I had here that experiment where I had that light bulb in there and I had water in there, but the light wasn't on. What does this tell you about that equilibrium? About that constant, that equilibrium constant? What does this tell you? It must be extremely small, okay? And exactly, we write that equilibrium. We had the H3O plus concentration times the OH minus concentration divided by water concentration divided by water concentration. This is close 1. So it's called the ion product of water, or the equilibrium constant for water is that concentration times this concentration. So this is a constant, and that constant is 10 to minus 14. It's extremely small. At 25 degrees. That's extremely small. That means this is mostly on this side. There's very, very little of this here dissociated into H3O plus and OH minus. And so if I have this and this in equal concentration, what would be if this is Kw is 10 to the 14, so then if I have H3O plus would be 10 to the 14 divided by a concentration of OH minus, okay? And this, or vice versa, 10 to 14 divided by H3O plus, and this is each 10 to minus 7. And 10 to minus 7, this is in the neutral point. That's when water, the concentration of H3O plus and OH minus is 10 to minus 7 mole, okay? It's very small, but very, very important. And why you will see in a minute. So now I can say, what can I say? I can say, So if I take the logarithm of this, I don't want to deal with all these exponents and stuff. I take the logarithm of this. What's the logarithm of this here? What's the logarithm of this? Negative 7, okay? So if I multiply this with minus 1, then I have 7. And we write a little p. That's not partial pressure. We write a little p that says, take the logarithm to base 10 and multiply it with minus 1. That's an instruction, okay? And so when I say pH, so this means take the logarithm of your H plus concentration, or your HVO concentration, and take the logarithm to base 10 and multiply it with minus 1. So what would be the pH here if this is pH? That would be pH. What would be the pH? 7, exactly. And what would be the POH? 7. We just have an instruction. Take the darn thing, that number, and take the logarithm to the base of minus 10 of that number and multiply it with minus 1. It can be a concentration. It can be anything. P of something. Never mind. Okay. And anyhow. And so pH and POH is 10 to the 7. That's an equilibrium. That's water. So pH and POH is 10 to, equals POH is 10 to the 7. You also can say that pH plus POH is what? 14. Okay. pH plus POH is 14. And this is a px scale that says P. So do something with that concentration of x or whatever it is, if this is a concentration, take the logarithm to base 10 and multiply it with minus 1. That's what this means. Okay? That's a px scale. And so if we have a pH scale, we say, the pH is minus the logarithm of the hydronium ion concentration, H3O plus. So if I have H3O plus equals OH minus, what would be the concentration at 25 degrees? It says right there, it's 10 to minus 7 molar. So I take the logarithm of this is minus 7. I multiply it with minus 1. I take the negative of that. So that is pH of 7. And at neutral, if you have equal concentration of H3O plus and OH minus in water, that's neutral. And this is pH 7. Now, let's see, if we want to have a pH of 0, pH of 0, so that would be here. What would we have our HVO concentration? What would it have to be? So the pH of 0 would be HVO plus, would be 1 times 10 to the minus 0. What's that? 10 to the minus 0. What's that? 1. And 10 to the plus 0? Also 1. Okay, no insult here. Okay, so that would be 1. Okay, that would be. And so your pH is then 0. Okay. What? Yeah, of course, you take the logarithm of it. So, of course, okay, you take the logarithm of 1 at 0. Okay, and plus and minus 0 is the same. So that would be the pH here. What would be the POH? What would that be? pH plus POH has to be 14 always at 25 degrees. What would be the POH? 14, exactly. So now we come to here. What's the pH of this thing here? What's the pH of this here? That's 14. What's the POH? 0, exactly. Now, if I have a concentration, a solution of 10 to minus 15 molar H3O plus, what's the pH? What's the pH? 10 to minus 15 molar H3O plus, what's the pH? 15, exactly. Did you know that there's a pH 15? No, because they say from 0 to 14. Not right. If you have a 10 molar solution, it will be 15. Okay, a 10 molar OH solution will be pH 15. So if you have a concentration of 10 molar acid, what's the pH? What's the pH of a 10 molar acid? Take the logarithm. What's that? -1. The pH is -1. Okay, you thought it only goes from 0 to 14. No, it goes from, it can be negative and can be above 14. Okay, that they didn't tell you at school. Somebody learned this in school, didn't they? Who did? Bless your teacher. Okay, very good. And bless the others too. Okay. So you're getting the hang of this. Now, remember water. What's the pH of water? What's the hydronium ion concentration, H3O plus concentration of water at 25 degrees? In molarity? 10 to minus what? 7. Okay, keep this in mind. Now I'm asking you a question. Which of the following solution has the highest pH? 10 to minus 3 molar sodium hydroxide, 10 to minus 6 molar HCl, or 10 to minus 12 molar HCl? Why don't you answer this and give me your answer? And I'm going to get Karen started. I have some cabbage here. We will make some indicator out of this, and I will get Karen to get started because I'm a little bit behind, as I see that, in time. Let's get it started. One has the highest pH. Think very carefully about that. Okay, you need to think this is bimodal. So it's many say A, and the others say no, it's 10 to minus 12 molar HCl. That's got to be the highest one. Why don't you think what 10 to minus 12 molar HCl means compared to water? Okay, I give you 1 minute, and you discuss it for 1 minute because then I need to move on. Otherwise, I can give you the test question. What's the concentration of the water? Yeah. Everybody's in? I'm going to stop it in 4 seconds. Everybody in, please. Everybody? One more? One more? So I'm going to let it go to the end, okay? Not that they say, you cut me off. All right, so it's a little bit more with A. Yes, of course it is A. So why is it A? Because 10 to minus 3 molar sodium hydroxide is OH minus is 10 to minus 3, H3O plus is 10 to minus 11, so that would be a pH of 11, okay? Now, 10 to minus 6 molar HCl is H3O plus is 10 to minus 6, that would be a pH of 6, but now here comes the trick here, not the hammer actually. 10 to minus 12 molar HCl is not H3O plus is 10 to minus 12. What's the concentration of H3O in water? 10 to minus 7. So you add 10 to minus 12 mole, this is 7.00001, okay? So that would be 10 to minus 7.00001. So the pH would be still 7. And water has already a 10 to minus 7 concentration. And this would be pH 7 if you add 10 to minus 12 molar HCl. It's such a minute amount that you add that it really doesn't matter. Okay, now let's go into an experiment. And the experiment is the following. Can you set up the eye clicker for me and keep it? So what you see here is, we could have the light, please. Let's have the light. Okay, I'm in the dark. The floodlight, thank you. Good. Come on. Huh? I told you. Can you put the lights on, please? I'm sorry about this. Okay, that's good. That's the fullest light. Now these one in the front here. Okay, I'm going to start. I have here, excellent, thank you so much. I have here cabbage juice. That's an indicator, a pH indicator. And here, so that's very organic, isn't it? And here I have muriatic acid, which is 30% HCl. So I add a little bit, beautiful red color, red for what? For acid. I have vinegar, it's less acidic, that's the weaker acid. Now I have aspirin. What's this? Aspirin is salicylic acid, isn't it right? It says as ingredient aspirin, that helps a lot. It's salicylic acid, and so this is here. Okay, now I have vitamin C. Vitamin C here. The colors are changing. Now I have club soda. Okay, cheers. And club soda obviously has carbonic acid. Isn't that right? So that should be slightly acidic. You put this in here. Slightly acidic. Now I have iodized salt. That should be more or less neutral here. Then I have baking soda. There it gets blue. I have washing soda. That's from the last century, middle of the last century, I think. It's Arm & Hammer, super washing detergent. Okay, let's use that. Let's go with the fashion here. And then I have ammonia. That's a strong base. And then I have drain cleaner, lye. That's a very strong base. And you see that? How the colors are changing. Isn't that beautiful here, huh? And so let's take a picture of me with this. Okay. All right, so now we come to the bonus question. And the bonus question is the following. Here's the bonus question. There it is. Do I need to connect it? Yeah, I need to connect it. Okay, there it is. Okay, now we started. Be quiet. No talking. We are the honor code here. Some countries think there's something different about honor, but that's a different story. Which of the following gases will have the largest deviation from ideal behavior? Nitrous acid, mercury, periodic acid, perchloric acid, or xenon? No talking, please. Just showing the fingers. Just kidding. Okay? And if you stay, I even give you the answer. The morning they just ran away. They had it. Okay. Let's go with D, huh? No, with C. Let's go with C, huh? I haven't got with anything yet, okay? So this is about intermolecular forces, and this is about volume of your molecule. So nitric is a strong intermolecular forces, it has H bonding. Mercury is a large atom, so that's a pretty big atom, so that's a large volume. HUI has strong intermolecular forces, and H bonding, and is a large atom, the largest of all of them. HCl4 has strong intermolecular forces, and H bonding, and xenon, wait, xenon. Xenon is a large atom, and with this, the answer was C. Okay. I see you on Friday.